It's quite important that to design algorithms that don't get tricked when the data is corrupted and is fraudulent. And as I said, sometimes the corruption in the data is coming from the strategic behavior, and there is a solution for that. In that case, maybe you need to not to change the exact data, and maybe like use some other version of the data that limit this manipulation from the other side. But there are also some other cases that, for example, you may have fake users or like these fake reviews or fake purchases in online platforms, and then you're still gonna use the data that contains all these like fraudulent activities in it, and perhaps those fraudulent activities cannot be really go detected. Some of it can go detected, but not all of it. So in that case, maybe we need a different solution. And there is in a recent work we looked at that problem, in particular for product ranking on online platforms. When as a platform we would like to show the right set of items to the user when they search for something, and on top of that I want to find the right order of the items of the items that I want to show to the customers. This is quite challenging for two reasons. First of all, the different ways that I can rank the items can be large, can be exponentially large. And on top of that, if I have this fraudulent data and fake user and fake reviews, it is not obvious if I can even like use the data to figure out which product has the highest quality score and which product has the lowest quality score. So, but I still want to use the data. The question is that how is it possible? Can I design machine learning algorithm that does not get tricked by these fraudulent activities? And the way that we answer that question is that we say, let's try to design an algorithm that try to be a bit conservative. So let's try that. So, this algorithm still wants to use the data, but not react to the data so quickly. It wants to be on the cautious side. But now the question is that to what extent I want to be cautious, because if I'm observing some pattern or some phenomena in the data, I want to react to that. And if I'm just not agile enough, I may lose the opportunity to actually do something nice here. So to what extent I want to be cautious, because as I said, waiting can be costly for me, and at the same time I also don't want to get manipulated. So there is this trade-off here. So in a hypothetical situation, let's say I know how much fraudulent activities are going on my data set. So in that case, we show that, okay, you know exactly to what extent you need to be conservative. Okay, so there is a right amount of conservatism that you can achieve. But usually this is not the case in practice, because if I knew how much fraudulent activities I had, that means that maybe I could go ahead and remove those. So then the question is that how can I still use that idea? And the answer is yes. We have this idea of parallelization. We came up with this multiple level of algorithms that they work in parallel. Each of them have different level of conservatism. Some of them, they react to the data so quickly, take some action. They recommend to take some action quickly. Some of them are like quite slow. They are very conservative and don't really react to some patterns or observation in the data. So we let these algorithms communicate with each other, and at the end, through their communication, they can figure out the right level of conservatism without even knowing the extent to which the data is corrupted. And that's the overall idea. And it turns out that when we did some simulation, even this version of algorithm that used the parallelization outperforms the one that has the full knowledge of the number of corruption in the data.